Let's go over the precise definition of a limit. So the precise definition of a limit, and let me just draw this graph here. And let's just do a simple quadratic, and we'll say this is the origin, although it should technically be here, and we'll draw it like that. So it's nice, simple parabola, whatever. So everyone knows the limit of a polynomial is just going to be plugging the function in, and as we know, x squared is just 2, so it's 4. So the limit as x approaches 2 is 4. So what does the precise limit state? The precise definition of a limit is a proof that basically states that if you can, hold on, let me try to move this. I really can't get this. Let me just break this into parts. It states that within a given interval of the limit, within a given interval of the function's limit output, there has to be a corresponding limit input. So for here, let's just say that it's 4 plus the limit output is going to be 4 plus 2, 4 minus 2. So if we correspond that here, that would be 4, 6, 2. So just intervals of minus 2 and plus 2. Now we have to find corresponding intervals. So here would be 2, or a in this case. And for a corresponding interval of 6, it would be square root 6. And for this one, it will be square root 2. So the precise definition of a limit states that right here, when there's 2, 4, 6, we see that there's an interval of plus 2, which we denote as epsilon. And here there's, I can't really calculate that mathematically, but there's a change in 6 minus 2, which is going to be denoted as delta. So let's get even more specific here. And let's take a function. It's going to be a polynomial again. Or I guess a linear function, same thing. Limit as x approaches 4. Actually, no, they use 3 in the book. 4x minus 3. Wait, yes. Not absolute value, actually. Is equal to 7. So, no, it's 4x minus 5, sorry. That's what they use in my book. So, if we draw this out, it probably looks something like this. Minus 5, probably somewhere around here. It's a little steep too. So it's probably going to look something like that. That means that as limit as x approaches 3, it's going to be 7. So if it's 7 here, there's going to be a corresponding epsilon at which the f of x interval is defined. So 7 plus delta and 7, oh sorry, it should be epsilon actually. I don't know how to draw epsilon. So 7 plus epsilon and 7 minus epsilon correspond to the limits 3 plus delta, actually 3, wow, 3 plus delta, and 3 minus delta. So delta is an arbitrary number. So this arbitrary number corresponds to how much the y changes. So here we can denote this as delta y, because it's how much the y changes from 7 to 7 plus epsilon, which is just epsilon because it only changes by a factor of epsilon when you just add the epsilon. Here, same thing. The only difference between these 2 points is 3 plus delta. So basically, we are finding that within this delta y, which equals epsilon, we are finding a delta, change in y. Here goes epsilon. We're finding a delta that corresponds to that change in y. So we have to find an epsilon which corresponds to a change in y within this given interval, which is plus epsilon minus epsilon, that corresponds to a domain, or delta x, that corresponds to delta. So let's prove this mathematically. Now, remember, what is the distance formula? The distance formula is just 2 numbers subtracted. So like 7 minus 4 has a distance of 3. They're 3 apart. So it's the difference. And the difference can be the same thing as the distance. So f of x minus L is simply just the function output minus the limit. So here, if we say that the limit is 7, this would simply be 4x minus 5 minus 7, which gives us the distance of any x inputted here from 7. So if we said 3, then it'd be 12 minus 5 minus 7, which equals 0. So that means at 3, the limit equals 0. Or sorry, at 3, the distance from the limit equals 0. So here we denote this as delta epsilon. So on that graph, if this is f of x, or L actually, this means, and this is L plus epsilon, sorry, this should be epsilon actually. That means from anywhere from this interval here, and also L minus epsilon. If you choose this point, right, which is, let's just say it's L minus 1. And that means if we do L minus 1 minus L, we get negative 1, and the absolute value, which equals positive 1, which is less than epsilon. So that means epsilon is probably greater than 1 here, although that was just an example. So the point being that for any value that you can make a ratio or an interval, so here it would be epsilon. So for any value or interval here, you can find a corresponding interval that matches the x value. So there will be a corresponding x interval that will give you the desired y intervals. Simple like that. So f of x minus L has to be less than epsilon because epsilon denotes the interval in which the limit will be found. So here it would be, if we did like that, for x minus 5, so if this was like the limit as x approaches 3, then within this interval the limit exists, and make sure it's continuous on this thing. So how do we prove it? So now let's get to the other definition, and the other definition is even simpler. It's x minus a is greater than 0 and less than delta, which is the corresponding thing. So that means the distance from x, so if we took that here, a and a plus delta, a minus delta, is x minus a is the difference. So if we chose here, then x minus a would give us this distance here. It has to be smaller than delta, which is the corresponding thing for the sigma. For the epsilon. So how do we find this? So first, what we're going to do here is plug it into these formulas. So the function here is 4x minus 5 minus 7 is less than epsilon. That's the same thing as 4 x minus 12, which is equal to 4x minus 3 is less than epsilon. So that means x, absolute value x minus 3, must be less than epsilon divided by 4. And x minus 3 is the same exact thing as this right here. So x minus 3 is in between 0 and delta. So that means x minus 3, so since delta is bigger, that means, one second. That means delta is smaller than epsilon divided by 4. And that is the proof and precise definition of limits.